This is Cosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to the Kosmographia podcast with Randall Carlson. We are joined, as always, by the usual suspects. Bradley, how are you doing this week, sir?
Evening, gentlemen. Yeah, quite good.
Doing good. What's that map you got behind you?
Well, this is something from the early '90s that really caught my attention, and got me kind of obsessed with the topography of the country and the idea that maybe it was washed over by a whole lot of water at one point, and kind of spurred on some of my desire to study this stuff. So it was serendipitous that eventually I ran into Randall, a couple of years later.
Yeah, it is quite striking, I have to say. When you put it up earlier, Kyle and I were talking about it. It is very interesting.
I'll send you
Mike.
a highly detailed version, and I'll put a link. I'll put a link up in the description for it.
Awesome. Yeah, that'd be great. Mike, sir.
Hi, guys.
How are you doing this week?
Where everything's normal in normal land.
All right. That's what we like to hear.
It's
Randall?
I'm doing well. But it is comforting to know that somewhere there is normality.
That's right.
As I said before, it's a relative term. I'm just normal compared to you guys.
Yeah, because there actually are people out there that are so normal that Mike would look abnormal.
My wife is one of those, actually. She's the most normal person I know, and God bless her for it.
Wow.
Yeah, well, I wasn't going to say anything, but I'd kind of gotten that impression. She's very sweet, though. You have a lovely wife,
sweet.
Mike.
That's right.
She is. She's a very sweet woman.
Except when she complains about spilling, food on her sewing area. When we're up in your studio.
Yep.
No, she's a sweetie.
Gotta be careful with the youngins.
Yeah.
There you go.
So, doing well. We're down to the wire on the restaurant, like I was saying earlier. And it looks like we're, 2 weeks or so away from being ready to open, which seems to be auspicious timing.
Yeah.
Yeah.
Yeah, it does.
Georgia has opened up.
Right.
Georgia's on the way. Yeah.
So I'm actually seeing some places that have opened their dining room. So, we'll see what happens, what becomes of it. Is there going to be a second wave that wipes us all out? I don't know, but
Probably not.
Probably not. Right.
Flagged.
Flagged. Yeah. Oh, yeah.
Banned.
We just got flagged. We mentioned it. We're not allowed to talk about that, right?
Let's talk about things that are 12,000 years old.
Wow, that's ostensibly safe, right?
Right. Yeah. So last week we were talking about microspherules, magnetic spherules, and we were going to look at what is the name of that stuff? Kyle had to look up how to say it.
Chatelairite.
Yeah, Le Chatelairite.
Le Chatelairite.
Le Chatelairite. Yeah.
Right. We're going to talk about Trinitite and some desert glass in Libya, and
all of that. Yeah. Well, also we didn't mention this, but framboids. And so while you're sitting there twiddling your thumbs there, Kyle, maybe you could look up framboids. F-R-A-M-B-O.
I'm going to get rid of these thumbs.
I got your framboids.
Framboids. Well, listen, don't knock thumb twiddling, okay? That's not a badge of disrespect.
Wikipedia, the term framboid describes a micromorphological feature common to certain sedimentary minerals, and particularly pyrite. The first known use of the term is ascribed to Rust, I don't know who Rust is, in 1935, and is derived from the French la framboise, meaning raspberry, reflecting the appearance of the structure under magnification.
Yeah.
See, Mike is much better at this job than I am.
and he's got listen to that French. Do that again.
I know.
I'm pretty good at twiddling my thumbs, though.
And we can sit here and twiddle our thumbs. It'll be great.
Well, I mean, look, thumbs need to get exercise too, right?
That's right.
People don't realize that this is important. You know? Well, look, you can laugh, but back when I was doing a lot of percussion, I regularly did all my, my finger exercises to keep my fingers in shape.
Yeah, you were playing a kind of drum where you really have to use the all the separate fingers on the drum too,
Yeah,
right?
yeah.
Mm-hmm. Yeah, I'm familiar with that. I play the djembe, so I know that.
Yeah.
But yeah,
Yep.
I watched the videos of you doing it, and you were a lot more technical and detailed than I was. But that kind of drum is like that, so
It is.
I totally understand. But still, twiddling the thumbs is a great pastime.
Yeah, I can spend
Drummers,
hours.
Mike. Drummers.
I got a joke. I got a drummer's joke for you if you want to hear it, but maybe later.
Uh-oh.
Okay, so yeah, I think I'll pull up a little share screen here. We're going to be looking at the petrography of particles and iron spherules from the Murray Springs, Arizona Clovis Age site. So the first image will be a backscattered electron image of a particle from the more than 400 micrometer magnetic fraction obtained from the basal portion of the black mat. Everybody now knows, I'm hoping, what the black mat is. So we're going to be
basal portion. Does that mean the bottom of it, or
yes, as in
okay.
the base. Basal is base,
right?
That's not the same as like basil leaves that you would sprinkle on your pizza.
Right. It's not an herb. It's a location.
It's not an herb, right? It's not. So the Murray Springs Clovis Age site showing iron spherules, and let me pull this up here so everybody can see what I'm looking at here. Okay, so this up here is, like I said, the backscattered electron image of a particle. And if you look close, you'll see there's a lot of little round white, real light colored features in there. And then B is a magnified version of A, where you can really see these rounded light areas. And if you look really close, you'll see that there's a texture. And this is where it comes with this raspberry texture, raspberry surfaced texture, right?
Okay.
And then you get to see, you've got a scanning electron microscope image of one of these, like right in the middle of this image up here, B, you see this circular feature. And then now you've got a scanning electron microscope image of that down here at C. And you can begin to see that texture that's so distinctive of a framboid. And so then in D, you've got the scanning electron image of the grains very, very close. Now, the thing that's interesting about this is if you look close, you'll see that a lot of them are cracked, right? You see the fractures in them? Can you see the cracking?
Yeah.
Okay.
Yes, sir.
These are very little dense particles that have been subject to tremendous shock forces. And that's why they're cracked on this level, see? So this is an example of what's being referred to as framboidal iron oxide. And found at Murray Springs, Arizona. This was published in by Mostafa Fayek in the Earth and Planetary Science Letters in 2012. So this very much supports the idea of an impact. And so the data.
So they
go ahead.
They didn't form during the like, how would they have gotten cracked from the forces? They weren't formed during it. They were cracked during it. Is that the idea?
I think they were formed during it. Here's what he says about it.
Okay.
The data obtained on the framboids from Murray Springs strongly suggests that they are not only of meteoritic origin, but that they are relics of a hypervelocity impact. The presence of the glassy matrix. Now that when you looked at the picture and you saw those round things, they were embedded in this glassy matrix, right? That's important. Is especially significant. Cosmic dust continually falls on the Earth's surface. It is made up of extraterrestrial particles, such as interplanetary dust, particles and micrometeorites. These particles can consist of smooth iron, silica, and glass, and framboidal microspherules, and particles in a crystalline matrix. Framboidal magnetite has in fact been reported from chondritic smooth cosmic dust. To our knowledge, however, framboidal magnetites, such as those reported here, have never been reported in a glassy matrix in cosmic dust. Now, what he's referring to there, cosmic dust, is this constant, gentle rain of cosmic material down onto the Earth. A lot of the critics of the impact hypothesis have tried to explain away the presence of these impact proxies by saying they are part of this constant, gentle rain of very small microscopic particles, cosmic particles, raining down upon the Earth. Thus, the particles described in this study are not consistent with samples from either terrestrial or unmodified extraterrestrial sources. Therefore, as the framboidal magnetites in a glassy matrix reported here are consistent with those found in some chondritic meteorites. While I continue on with this, Mike, why don't you look up a chondritic meteorite so we can define that for the listeners so they understand what a chondritic meteorite is.
Yeah, I've heard them they're called them carbonaceous chondrites.
Yes.
Is that right?
CHONDRITIC, chondritic, or chondrite, like just look up chondrite. So therefore, as the framboidal magnetites in a glassy matrix reported here are consistent with those found in some chondritic meteorites and inconsistent with known terrestrial sources. It is possible that they could have formed as the result of the high energy destruction of an appropriate chondritic meteorite. Together, these data suggest that the framboid particles are the product of a hypervelocity impact event. Its spatial extent remains to be determined. So I think the answer to your question is that they would have been brought in by a meteorite, and in the process of this hypervelocity impact and the explosion and the violence of the explosion of this chondritic meteorite is where you begin to see the shock effects, the microscopic, microscale shock effects.
Okay.
Analysis of the data presented in this paper clearly shows that the framboidal particles obtained from the Murray Springs site are not consistent with known cosmic dust or terrestrial materials. These particles occur in a glassy matrix with an unusual chemical composition. They are structurally complex and contain significant internal layering and strong fracture patterns. Such fracturing could reflect shock damage that occurred during an impact event. These data suggest that the observed textures are not due to hydrational expansion, that is, by taking on moisture, but to a shock event that fractured and largely amorphized the grains as a whole and melted and contaminated the matrix. Therefore, we argue that these particles are the product of hypervelocity impact event. The exact nature of this event and its spatial extent, however, remain to be determined. So this was in 2012. Look at this. Yes, we are viewing Mike's screen. Look at this. Yes, 700-gram individual of the, let's see, NWA 869 meteorite chondrules and metal flakes can be seen on the cut and polished face of this specimen. So it says this is an ordinary chondrite. So Mustafa Fayek is saying that these particles that he's examining would be consistent with delivery of the infall of a chondritic meteorite, and then subject to the tremendous shock forces that would accompany. And of course, the point is, because where is it found? It's found at the base of the black mat. So that puts it right, boom, right smack there at the Younger Dryas. So Younger Dryas Boundary, I'll say, the onset of the Younger Dryas Boundary. And then we talked about also that year 2012, Isabel, if that's her name, Isabel Alcantara. the discovery in Lake Cutzio, central Mexico. And this is happening. This was, I think, her work was published in March. Fayek's work was published in, let's see, I don't know, but around that same time in 2012. We won't get back too much here into the Mexico work, other than to reiterate the thing about the critics who remember when we talked about this a number of episodes ago, when the critics looked for the Younger Dryas Boundary magnetic spherules at the at the black mat layer, and as Alcantara says here, that they reported finding no YDB magnetic spherules, although claiming to follow the protocol of Firestone et al. For quantification of magnetic spherules, and concluded that Firestone et al. Misidentified and or miscounted the magnetic spherules. Later, Lecomte, now remember Lecomte, we've talked about their work and the important work that basically rebutted the critics. They rebutted the rebuttal, if you will. Malcolm Lecomte was the man we brought on. We had, who joined us on the Joe Rogan podcast with Michael Shermer. So if people have watched that, the fellow that we had that was, and whose work I was showing at the time, is who's being referenced here. And we met Malcolm. Brad and I managed to spend a weekend with Malcolm down there at the round table in South Carolina. Yeah, at
it was Wilmington.
Wilmington, right? When we were down there examining Carolina Bays with those guys, and with George Howard and Chris Moore and Mark Dimitroff and others who were part of the Comet research team.
Yeah, Tony
great guy.
Zamora was down there with us.
Yeah, Tony Zamora was there with us, right? And we probably need to get him on the show at some point, and I'm sure he'd be more than willing.
We definitely will.
Yep. So later, Lecomte et al. Independently examined two Younger Dryas boundary sites common to Firestone et al. And Surivel et al. They reported that, quote, spheral abundances are consistent with those of Firestone et al. And inconsistent with the results of Surivel et al. They also concluded that Surivel et al. Altered the prescribed magnetic spheral protocol in fatal ways, particularly by not observing requirements for sample thickness, sample weight, and size sorting. We consider these discrepancies significant enough to negate the conclusion of Surivel. And then we will go to...
I don't want to derail us here, but I just wanted to point out Dr. Martin Sweatman talked about these this sort of argument, the various ideas about the microspherules.
Mm-hmm.
And there was an idea of, how spherical. And the Comet research team was a little more, liberal on how spherical they were, right?
Yes.
And the other team was like, well, it's not a sphere. Or, there's no... So Dr. Sweatman's point was, since there's really no way to sort of quantify how spherical it must be or measure this, then he just kind of, his idea was like, well, let's just go ahead and set this paper aside because we can't argue either way.
Mm-hmm.
You see what I'm saying? Oh, you're not spherical enough. Well, you're too spherical in terms of like which ones they were collecting and how and counting.
Well, I mean,
I thought that was a good point.
From what I've seen and looking at these impact proxies, perfect sphericality is not a requisite. I mean,
yeah,
you can have near perfect sphericality, but you can have all kinds of distorted and distended shapes. And yeah, so if you establish this extremely strict criteria that, we've got to have perfect sphericality, well, now you're excluding a whole class of objects that could have been produced through melting or through shock effects that are indicative of an impact, but you're now excluding that. So that in itself wouldn't be enough to like Martin Sweatman was saying, that in itself is not enough to sway the argument one way or another.
Right.
But when you fold it in with all of the rest of the arguments, the failure to follow the protocol specifically that
Right,
Firestone
yes.
set out, the fact that, and we haven't talked about this, the sampling locations, which when we get back into the nanodiamond thing, and one of the great papers that really moved the acceptance of an impact event forward was one of the major studies on the finding of nanodiamonds, and in there they address the problems, additional problems, which mostly were sampling problems. So not only aliquot size too small, the size sorting was wrong. The usage of electron or technologies to perceive at the level necessary. Also, the sites where samples were taken were not in the right place. So, that's a big part of it as well. So one of the other really interesting and important studies that came out in 2012 was by Ted Bunch and 17 others, all who are members of the Comet research team. And it was published in the Proceedings of the National Academy of Sciences. It came out on July 10th, so we're moving through the year. The title of their paper was Very High Temperature Impact Melt Products as Evidence for Cosmic Air Bursts and Impacts 12,900 years ago. And so they go on to say that it has been proposed that fragments of an asteroid or comet impacted Earth, deposited silica and iron-rich microspherules, which we were just looking at. That's what we were just looking at in the graphics, and other proxies across several continents, and triggered the Younger Dryas cooling episode 12,900 years ago. Although many independent groups have confirmed the impact evidence, the hypothesis remains controversial because some groups have failed to do so. We examined sediment sequences from 18 dated Younger Dryas boundary sites across 3 continents, which included North America, Europe, and Asia, okay, spanning 12,000 kilometers, okay, around nearly 1/3 of the Earth. And 12,000 kilometers is right about 7,200 miles, okay, spanning 12,000 kilometers around nearly 1/3 of the planet. All sites display abundant microspherules in the YDB, with none or few above or below. In addition, 3 sites, Abu Huraira in Syria, Melrose, Pennsylvania, and Blackwell, South Carolina, display vesicular, meaning vessels, right? Just like you would find in scoria, volcanic rocks, right? So they display vesicular, not testicular, vesicular, high temperature, siliceous scoria-like objects, or SLOs. So here's another, insider term we can use, SLOs. Mike, you want to look up scoria for us? SCORIA, or Kyle, whoever. SLOs. So these are scoria-like objects that match the spherules geochemically. All right, what'd you find for us, Mike?
Hang on a second. I'm loading it now.
Okay. This is
since we got a pause here, or we can make a pause when I'm editing. We did do this last week, and the next 4 or 5 slides from this paper.
Yes, but it's good stuff. So
no doubt.
Yeah. But we're see, and here's the thing, some people may not like the redundancy. I think it's important because if you really want to learn this stuff, you've got to go over it several times. Otherwise, it just slides off. And then when we go forward, looking at the individual pieces, if you forget the individual pieces, it doesn't make sense when we start putting it all together. But here we've got the scoria-like objects. So there's vesicular. Beautiful. Yeah, look at this.
So pumice.
Yeah. Mm-hmm. And so these are produced from, melting. And, when it crystallizes, you've got the gases inside, they can discharge, the volatiles can discharge, leaving the Swiss cheese effect. And I think we did look at some of the objects from the very high temperature impact melt products. I'm going to do a share screen. So as soon as Mike's done. Yeah, but look at that. That gives people a pretty good idea of what we're talking about with scoria-like objects, SLOs. Yeah, here we go. I believe we did briefly look at this last week, right?
Yep.
Yeah.
We did.
Okay, so there you go. At the top are your SLOs, your scoria-like objects, and at the bottom are your magnetic spherules. So these are the fingerprints that we're talking about. Fingerprints of catastrophe. And to me, what we do is we look at the fingerprints and we look at the footprints. Okay, so then, but there was a lot of stuff I think we did not cover. Did we talk about the importance of melted silica glass? I think we did, yeah, because that's where we introduced the lachatellite.
Right, and the boiling of the quartz.
The boiling of the quartz.
Right. We got that far.
We did get that far. Okay. Yeah, I like that. The boiling of the quartz.
Yeah, 2,200 degrees Celsius or 4,000 degrees Fahrenheit.
Oh, you guys are just awesome.
Right
okay,
on.
so Brad, I know Brad knows that, but still I try to remind him from time to time just in case he.
Yeah, Brad, what's the boiling point of quartz? Test.
3992 and above.
Oops. Okay, let's go to. Here we go. Let's go to this one. I don't think we looked. Did we look at this one?
No, not last week. That's a new one.
Okay, good. Okay, so now we're on to the new stuff. So we kind of, picked up, segued from, kind of where we left off last week to get into the new stuff so that it kind of helps to bridge and make a little continuity here. So here we have.
And you had said that we were going to look at it much in closer detail. So here we definitely have it.
Good. Here we go. So you've got your your scattered electron microscope and backscatter electron images of impact pitting. So this is from Melrose, Pennsylvania here, and cluster of oblique impacts on a scoria-like object, or SLO, that produced raised rims. So in other words, even on a micro scale, you still got all of this stuff, under extreme high pressure, velocity, crashing into each other, right? It's part of what's going on in this maelstrom of violent, in this violent plume of impact generated stuff that's going on in the atmosphere, right? So when you look at here, like one, it's pointing to the raised rims, just like you would have with a larger crater on Earth. You have these raised rims. And it says tiny spherules formed in most impact pits together with irregularly shaped impact debris, which is number 2. Now, when we go to B, this is interesting. This is from an Australasian tektite, which is about 700 and some thousand years old, just by comparison, right? Oblique impact produced a raised rim, which is number 1. And then you have right here a tiny spherule in the crater bottom. Now, I want you to look at this oblique impact, the shape. Is with a raised rim on one side, does that kind of.
Yeah.
Does that look familiar? Have we seen anything like that anywhere?
Oh, yeah.
Somewhere near George Howard.
Cheese.
Somewhere. Where is George when we need him? Yeah. I mean, look at this. I mean.
Right away you see that.
Right. And this is probably the object here, which is actually preserved, coming in from this way, producing an oblique impact, and then down, downfield is the raised rim. So yeah, this is highly suggestive. It's like a micro scale Carolina Bay.
Yeah.
So if someone were to
micro.
dig next to that raised rim in a Carolina Bay, maybe the object would be
Yeah,
there.
find a giant ball down there. Yeah.
No, because probably if those are, and we're going to get back to that. We're going to have a whole
Yeah.
couple of episodes about the Carolina Bays. If they were impact produced rather than ice boulder produced, or some of the other theories, the impact would likely have vaporized on impact. Or maybe
air
not
bursts
even
produce.
see. And here's the other thing that I raised a question of when we kind of briefly touched into the Tunguska event, which obviously we're going to come back to. Under the epicenter of the Tunguska explosion, there were shallow elliptical craters where they produced somehow by the pressure striking the ground. I don't know. But
Yeah.
there are features there.
Shockwave or something.
And what?
The shockwave, maybe, or something.
Yeah.
I don't know.
Yeah, they called them the cauldrons. Right?
Yeah. Well, the whole area of 200 square miles that was pretty much incinerated under the blast zone was what was called the cauldron.
Oh, okay. All right.
Right.
This is like scale invariance, though, right? This is these tiny impact craters.
Yeah. Here you go. Yeah.
Yeah.
It is very much scale invariant stuff. All right. Then we go to this. This is, again, a scanning electron microscope and backscatter image of collisional particles. So now here, look at this over here on the left. Now this is back from Lake Cutzio in Mexico, right? So here you have, and notice the scale down here, 20 micrometers, right? So these things are tiny. So here's two spherules that collided in flight, and then they fused together. You see that?
Yeah, that one on the left there looks a lot like when you see those images of the atomic bombs detonating, when they're first right in the very beginning.
Oh, yeah.
It
Yeah,
kind
they
of looks
do.
like that with the shell.
They certainly
multi-layered. It's weird.
Yeah, here's what they're saying, that the left spheral, and you can see this kind of depression around it like this. They're calling that plastic compaction to form a compression ring. So during the impact, one of them sort of was compressed, collapsed on itself, and it formed this trough, if you will.
Right.
So that's what number one is pointing to. And then number two is another compression ring. And then number three is pointing to a line of gas vesicles right here. And a splash apron, number four. So if you look closely here, you'll see that there's like melted stuff that kind of went splooged outwards as a result of this high velocity collisional impact of these two microspherules. So that's called a splash apron. So another cool new term for
I'll
us.
have to remember that.
Yeah. So one of these episodes, Russ, you'll have to don your splash apron.
I was just gonna say I can, if somebody drops something in water and it splash hits me, I can be like, "You hit me with the splash apron." I can use that term.
I'm sure you're going to find many and multiple uses
Right.
for this new term. No,
Fantastic term.
Okay, B is Kimball Bay. Collision of two spherules destroyed one spherule. So here you can see number one is a spherule that's been destroyed, literally destroyed because of the violence of that impact. And then formed a splash apron on the other, which is number two is pointing. Here's the splash apron. You can see it right here. If you can hopefully see my mouse, number two is pointing to the splash apron. This destructive collision suggests high differential velocities of tens to hundreds of meters per second. So that's pretty darn fast.
And the pattern on that on B there, that you up to the left of this and up above the splash apron, you can see this kind of
turtle shell
pattern. It's
Yeah.
interesting.
Yeah. Oh, yeah. Right. Exactly. This. Yeah. You can see that. And that is most likely the result of the fact that for a very short period of time, the surface of this thing was molten and then it was rapidly quenched.
Right. It was
Formed this
crystallization.
pattern. Yeah.
Yeah.
So are they mostly hollow? Because that one that's impacting, you can see the interior.
Yes, not mostly hollow, but some of them are hollow. And I don't know in this case, maybe not, but this. You can
Yeah, the one that got destroyed was definitely hollow. Maybe the other
right,
one's
the other one's
solid.
solid. That's really cool.
Yeah. So this right here, notice this coming down here. Here's you've got this stuff coming down this way. So all of this right here was part of a microspheral, and during the impact, it was destroyed. Presumably, the one that wasn't destroyed was of a higher density, maybe with a slightly different composition. So it was not destroyed. Now let's look
Talk
here.
about scale and variance. Yeah, I think somebody was looking at images like these when they hypothesized that the moon is had a second object come up and attach itself to it and kind of overlaid part of the sphere that was already there. I don't know if you've seen that. I saw that
No, I
several
haven't
years
seen
ago.
that, Brad.
Yeah, I think they were looking at pictures like this and got that idea.
Huh.
I'll share that with you.
Okay, yeah, because there,
Basically, what he's saying is talk about the moon. I think that's what he's saying.
one day,
Subtle,
Okay.
subtle,
One
Russ,
day.
subtle.
one day when the world is ready, we will talk about the moon. Okay, let's go on. So figure 12, look at A, that's some of your Libyan Desert Glass. And as it says, it's displaying tubular glassy texture. You see the tubules?
I do see it.
Okay, I think we just got an important message from one of our co-sponsors. Okay, is it close to break time? It is? Okay.
Anytime you want.
We will look at this slide. So B is again in Syria, Abu Huraira. I'll get it down. Just give me a few more years. So here you have the La Chatella. Mike, help us out here with your French.
La Chatellierite.
La Chatellierite. That's very close. La Chatellierite. The end of it is liarite. Right? I got that part of it. La Chatellierite. That's it. La Chatellierite. Got it. La Chatellierite.
Well,
Everybody listening, repeat after me 150 times. La Chatellierite. Oh, what? Am I not right, Mike?
That was different than what I found, but hey, I think it sounds better than what I found.
Listen, you know what? I actually did look up how to pronounce this, and I heard like 3 different pronunciations, and every one of them was different.
Yeah.
Yeah, I like the one you're using there. La Chatellierite.
Yeah.
La
That's
Chatellierite.
That flows off the tongue. You know, that's lyric worthy. I mean, you could put
Yes.
that in a song, you know.
We could put
I
that.
love
Yes.
La Chatellierite.
So
do this.
Okay, next week, Kyle.
But La Chatellierite is not, that's not lyric
Yeah,
material.
that's
That's
not
not
very
poetic.
Chatellierite. Yeah, it's not.
Yeah.
La Chatellierite.
I like that. Yeah, let's go with that.
Yeah.
Okay, we'll go with that.
Huraira, I think is how the other Abu Huraira.
Abu Huraira.
Yeah.
Abu Huraira. You know,
There's a lot of different pronunciations of that one too.
There
I
is.
actually asked a guy who spent a lot of time over there, and he was like, "Pick one."
Yeah.
So, Huraira.
Pick
or
one.
Huraira.
Yeah, pick one. Okay, so all of you people, I've noticed now that sometimes people post things that says Randall is mispronouncing some word.
Yeah.
Oh yeah, the
Or
Homo
another.
correctus.
Oh, yeah. You're getting Homo correctus.
Oh, Homo correctus. Well, look, I like to pronounce words correctly when there is a correct pronunciation. But when you have 2 or 3 or 4 different pronunciations, what's the town there near you, Brad? That's the county there near you that's pronounced Leicester, right?
Oh, yeah.
Now-
I was thinking Transylvania, but yeah, Leicester.
Well, okay, I say Leicester. Everybody would think like, Lester, Leicester, right? But it's actually Leicestershire, right?
Oh God. Yeah.
Yeah.
In England, yeah, it looks like
In England, it's the same word as
Leicester.
Leicestershire.
L-I-E, yeah, Leicestershire.
But they're all the locals says, "Hey man, let's go on up to Leicester." So which is right? I don't know. Do the
Right.
locals, I'm going to go with the locals just because Leicester is a hell of a lot easier to say than Leicestershire. It's like, is it Worcester sauce or Worcestershire sauce? However you pronounce it, it tastes the same. Okay.
Worcester.
Worcester.
Are we on break?
Yeah,
What's
we're
going
taking
on?
a
No,
break.
I think we're degenerating rapidly here, so that's probably a signal it's time for
That's
break.
right. Break
We'll be
time.
right back, folks. Thanks for
There was a
watching.
distraction.
Worcestershire.
All right, welcome back. Let's jump right back into it, as you said, Randall.
Jump right back into the maelstrom.
That's right.
The maelstrom of information. Well, let's do then. Doggone it. I'll just go right back to screen share here. And we will pick up where we left off. Yes. So we're comparing the Libyan Desert Glass on the left to the with the tubular glassy texture to the Abu Huraira La Chatellera. You know what? I'm going to just take a day off of work tomorrow and just practice saying that all day until I have it. La Chatellera. Anyways, we'll call it La Chatellera. Yeah, La Chatellera.
La Chatellera.
La Chatellera. That was as we came.
Yeah.
La Chatellera. That was it.
That's
La
right, yeah.
Chatellera. Okay, everybody repeat after me 1,000 times. La Chatellera. Okay, that's enough for now. Okay, so then we have B, which is from Abu Huraira, and it is disturbed by chaotic plastic flow and embedded in a vesicular calcium oxide rich matrix. So there it is. So Abu Huraira and the Libyan Desert Glass. Let's see. Be nice to get a date on that. What's the latest dating? You want to, Mike or somebody? One of you people out there in Neverland, look this up.
Looking up. What you got?
You're looking up Libyan Desert Glass.
From like 2,300 years ago, or are you talking?
No,
much older?
it's much older than that.
Okay.
And so here, what you have, this is being interpreted as evidence of an atmospheric detonation, releasing tremendous amounts of thermal energy and literally melting the surface of the desert. Okay, that's your Libyan Desert Glass. Mike's going to give us a date on it. I had the date at my fingertips.
26 million years.
Sounds about right. Although I'm wondering,
Right, 26 million years ago. I forgot to press my button.
Okay. Yeah, Mike, when you're doing this, you cannot forget to press your button.
Thank you, Randall.
Man, it was used to make tools. It was
Yeah.
napped.
Yeah.
Oh,
Yeah.
God, look at that stuff.
I would love to find me one of them heads.
Wouldn't that be cool? Mm-hmm. Yeah. So think about that, man. And the temperatures have got to be up a couple of thousand degrees Fahrenheit, at least. And what's this? What's the aerial extent of it? Is it about maybe 7,000 square miles? Does that sound about right?
I have a map if you'd like me to share it.
Well, sure. Why not? Yeah, that'd be great. I like this. This is very satisfying that Mike, you see, he was being called Silent Mike.
All right, you have to stop your share.
Okay, I will stop my share, and Mike will share his screen, and we will see the aerial or geographical extent of it. There we go.
Yeah, and I found it says several thousand square kilometers is the extent.
Several thousand. Okay,
Yeah.
so I was off.
Literature values on the extent vary between about 2,000 and 6,500 square kilometers.
Oh, okay.
yeah.
Yeah, okay, yeah. So flash that back up there again, Mike. So we can see the extent of. So part of it is in Egypt, part of it is in Libya. hence the term Libyan Desert Glass. Well, there you can see its relationship to Egypt. You see Cairo up there. You see the Nile River along the northeast quadrant of this image right there, and you see Cairo up there, which would be the site of the Great Pyramid. So I would guess, wouldn't be surprising that some of this Libyan desert glass found its way into, into the Egyptian, perhaps using it in jewelry or effigies or whatever. Be something interesting to research. And I may have seen something on that. I cannot recall right now, but I believe that there is some finds in Egypt where they were using the Libyan desert glass. Okay, that's pretty good. Now I'm going to go back to my share screen. Here we go. So here we've got this comparison between Abu Huraira and Libyan desert glass. Abu Huraira, presumably 12,900 years ago. Libyan desert glass, as we just learned, 26 million years ago. And yet the assumption here is very similar. The idea of the genesis of the material at Abu Huraira. Notice it's calling lachatellite tubes. When you have a volcanic eruption and you have a very fluidized magma that comes out, you oftentimes will form tubes, on the macro scale. And Brad and I have visited craters of the moon in Idaho, right on the northern rim of the Snake River Plain, and there where you have the quite recent volcanic eruption. In fact, volcanic eruption going back around 10, 12,000 years ago, that spilled out this highly fluidized lava onto the surface of the earth. And as it cooled and crystallized, it formed tubes. And some of these, I think, did we even go in one of them, or are we trying to remember now? You remember the tube?
I don't think so at Craters of the Moon. I'm remembering down there near Flagstaff and Wapatki.
Yeah.
That cinder cone down there, there were some lava tubes. That's what I'm thinking we went in.
That might have been
could have been some there up at Craters of the Moon, because Wilbur was with us on that trip, and I remember that picture of him. So
yeah,
it was more of a cave than a tube, I think. But yeah,
it was like a cave. I mean, and it was more or less oriented horizontal, actually. Yeah, and I think there was a lot of those there in Craters of the Moon.
So those tubes, those lava tubes, form after the flow is over? I thought.
Well,
I had the idea that they formed and the lava's flowing through it with the solid out exterior.
Well, I think that they form, as the lava is cooling, or as the molten material is cooling.
Okay.
Okay, so now we get to the Trinitite, and here you have an assortment of backlit translucent Trinitite shapes. Number one is called an accretionary, because notice what you've got there is a spherulitic form, and then two more objects have accreted to that. You see that, the idea there? You've got the spheral, and then one and another under the high temperature, high pressure gets slammed into it, and then accretionary means it accretes, right? Accretionary. So then it gets welded onto the larger one. And so number one, spherulitic, or number two is spherulitic. Notice number two is very elegantly spherical. And then number three, right here, broken teardrop. You see they've cut off the tip of this thing, but you can kind of see if you took it, it's broken. So undoubtedly, again, evidence of likely the shock pressures, but then that tip, see, so it's rounded at the base, but then it's pointed like a teardrop. So this is a very typical shape that you find in these byproducts of these high energy events. For example, tektites, which we'll be looking at pictures of, you'll have teardrop shapes are quite common. And tektites are molten, crystallized out of the molten, presumably passing through the atmosphere, taking on those shapes as they crystallize. Then number four, bottle shaped, right? So what they're doing is they're showing out here the diversity of various shapes that these things can take. Number 5, dumbbell, and you do actually see sometimes in tektites very distinct dumbbells where it's like almost like two sphericals, but they're welded together by this much narrower dynamic diameter section, and have this very much dumbbell-like appearance.
Or it's like a spinning droplet or something that
Yeah.
it's like stretching
Mhm.
apart and having the two spheres on the end.
Yeah. And then number 6, as it says, is elongated or oval. Then when we get over to B, that's your edge-on view of a pancake trinitite with a smooth top. Number 1, there's the smooth top, and a vesiculated interior. Number 2, showing here you see the vesicles, the hollow spaces, and a dark bottom composed of partially fused rounded trinitite objects incorporated with surface sediment. So it's picked up some of the surface there that has been fused onto the bottom of this particular piece of trinitite. So this is just by example for comparison to impact proxies. And interestingly, by studying the effects of these nuclear weapons explosions, we actually do gain a lot of insight into cosmic impact phenomena. Even cratering, things both on the micro and the macro levels. And so we're going to have an episode where we really look in depth at the whole nuclear testing program and extract some insight that will help us understand these the cosmic processes that we're trying to learn about here. All right, check this out. There's a piece of Libyan desert glass right there. So the origin of desert glass is uncertain. Meteoritic origins have long been considered possible, and recent research links the glass to impact features, such as zircon breakdown, vaporized quartz, and meteoritic metals, and to an impact crater. Some geologists associate the glass with radiative melting from meteoric large aerial bursts, making it analogous to Trinitite, created from sand exposed to the thermal radiation of a nuclear explosion. Libyan desert glass has been dated as having formed about 26 million years ago. Like obsidian, it was knapped and used to make tools during the Pleistocene. So again, during the Trinity that was the first testing of the atomic bomb in New Mexico. And like Tunguska, which exploded in the atmosphere, the Trinity explosion was, I don't remember the exact height of it, but it was well up into the atmosphere. Because if it hits the ground, like in the case of an impact, if it hits the ground, a lot of it's still going to be enormously destructive and violent, but a lot of the energy is then absorbed into the earth itself. Whereas if it blows up in the atmosphere, there's nothing. I mean, the radius of destruction is going to be much greater. And so when they tested the atomic bomb, I mean, they were assuming, the physics of it told them that, well, if we detonate the things in the atmosphere, they're going to be more destructive than if they actually hit the ground and explode. And so both the Hiroshima bombs and the Nagasaki bombs, people might think, oh, you drop a bomb, it falls down, and then it hits the ground, hits the earth, and then it explodes. But no, these things were set to actually explode in the atmosphere so that the radius of destruction was maximized. Okay, so that's our Libyan desert glass. We know the timing of it about 26 million years ago, which is interesting. 26 million years. That would be, let's see, 26 million years. That would be 1,000 precessional cycles of the Earth, for whatever that might mean. Just an interesting little coincidental sideline.
Yeah.
1,000 precessional cycles. And when we get into getting into looking more at the archaic and ancient traditions, and we really delve into the ancient concept of the great year, then we will find this recurrence of the multiples of the Earth's precessional cycle of 26,000 years. Okay. And here's another image of Trinitite in its more raw form, also known as atomsite or atomsite. I don't know how to pronounce that, or Alamogordo glass. It's the glassy residue left on the desert floor after the plutonium-based Trinity nuclear bomb test on July 16, 1945, near Alamogordo, New Mexico. The glass is primarily composed of arcosic sand composed of quartz grains and feldspar. We don't need to get into all of that. It is, as it says, mildly radioactive, but safe to handle. Now, again, the point here is that the Libyan Desert Glass, what do you got? You've got this melted sand sheet from a presumed atmospheric explosion. So it's being compared to what Trinitite, which was formed by a plutonium bomb explosion in the atmosphere that was hot enough to melt the sand. So you see there's these parallels between these two features. And let's see, why do I have a picture of Houghton impact structure? There's Meteor Crater. Okay. Well, there's a reason why I must have Houghton impact structure here. Undoubtedly because impact proxies were found there. When I put this together a number of years ago, I had a reason, and I think it's because there were microspherules associated with this particular structure. Anyways, and then there's of course Meteor Crater. I've noticed
I think it's mentioned in that bunch paper.
Yeah, it is. It is mentioned in the bunch paper. So then the Meteor Crater, which is not quite rounded, but a lot of people have pointed out and made the claim that, well, it would not be impact produced because it's not perfectly circular. But you got to bear in mind that the shape of the crater is also going to be affected by the lithospheric structure of the target, right? So if you've got fault lines and things, if you've got any kind of a rectilinear pre-existing fracture pattern, you may not necessarily get a perfectly rounded crater. In this case, I mean, it's pretty damn certain this is a meteorite since pieces of it have been found, and it's a meteorite, right? And it's an iron meteorite that's just like all kinds of other iron meteorites that have been studied. And it hit the earth and excavated this crater. So now we're getting to light photomicrographs of magnetic and glassy spherules from Melrose, Pennsylvania. Shapes include spherules, ovals, teardrops, and dumbbells. And colors include clear, gray, red, brown, and black. Note that spheral B, look at this, spheral B, we've seen a picture of that before, right? But let's come back to it, contains a large bubble. And then you've got D, look at here, here's your dumbbell kind of shape. Look at D and H, where you've got two spherules that hit with such force that they just welded together. That's clear evidence of non-normal processes. It's clear evidence of very high energy processes going on here. So if you find these things, like in Melrose, Pennsylvania, where they're found right at the base of the black mat at the Younger Dryas Boundary. So you have to be able to come out and be able to explain what kind of a high energy event could produce things like you see in D and H.
So the typical regular infall of cosmic materials don't have these characteristics?
No, because it's a very gentle process. You got to imagine this little microscopic grain just, gently falling to the earth. And, these things are raining down, but they're widely dispersed. And again, it's not a high energy. There's nothing that would cause two of those spherules to be forced to weld it together. just like here, it says D and H indicate the fusion of molten or semi-plastic spherules.
Right. So they would have had to have formed in some other high energy impact somewhere else to rain down on the Earth in that
Yes.
form. Right.
Right. But they're not found in this form.
Okay. Right.
So that's the whole point. I mean, that's one of the characteristic things that you immediately can differentiate and say that these are not the normal rain of cosmic material to Earth.
Okay.
Because you don't find this. And if you did, yeah, it would have had to have been created somewhere else.
Right.
Which is probably not out of the question. But note, as it says here, that H consists of two dissimilar accretionary spherules. The clear one is silica rich, so it's almost like clear glass, and the other is iron rich. So on the left, silica rich, on the right, iron rich. And then here, G, look at, there's your teardrop shape. Interesting. And then the different colors, which of course are going to be a function of composition. But these are the kind of things you look for under the microscope. And they're tiny, tiny. So you have to be very diligent about your sampling and what kind of technologies that you use to identify these things. It's one thing to see actually what they look like, and then something else again to be able to actually determine the cosmic chemistry of these things. All right. A on your left, a pooled Trinitite. So this is what it looks like on the desert floor. In situ Trinitite on the ground after the Trinity nuclear bomb detonation. Width of the view here is about 20 inches, and B is a large piece of Trinitite, and the up side you see was upward facing as it lay on the ground. So there we go. So we'll stop screen share there for now. We have actually already looked at this paper, which is an excellent paper. So we can learn about these high energy events by looking at nuclear detonations. You recall that our discussion of the Oralton Farms mastodon, just to kind of go off on a tangent for a moment. Remember the Oralton Farms mastodon discussion?
I remember two of them. One of them was, which one?
The one that was crushed where the foot was in place.
Yeah, the footprint.
That's the one I'm talking about. Yes. So here you got a picture of mastodon ambling across the through the forest floor, because mastodons were probably in the forest because they were browsers. In other words, they like to eat branches and leaves and things like that. Whereas mammoths were grazers. That's an important distinction between the species of mammoths and mastodons. Anyway, so this mastodon is walking along, and the ground is soft. So as he's walking, his feet are sinking into the ground, maybe 4, 5, 6 inches, 8 inches. Mastodon's going to weigh 4 or 5 or 6 tons. So he's pretty heavy. He's going to sink into the ground if it's soft at all. Now, all of a sudden, some force knocks him over. Both of the femurs are snapped, right? The entire skeletal is forced, probably pushed ahead, and the leg shears from the foot, which is embedded into the ground, right? Okay, so in trying to picture what kind of a force could produce such an effect, again, we can turn to the nuclear testing, and we'll find out some pretty. We've got so
this is like shockwave forces, right? I mean,
yeah,
yes,
they're at such high pressure that they start traveling faster than the typical speed limits of the medium, because they're creating a new medium.
Yeah. Okay, so here I would suggest is what we're talking about. Here we go.
Yeah, I see your point. I see what you're showing there. Yeah.
Yeah. Yes.
You get set on fire, and then the shear forces the shock wave comes across, and
Yes.
yeah.
And the shear forces just are moving actually horizontal.
Right. Yeah.
Yeah.
And that's
And
what
you
we
can see it actually pull back, like right after that. It goes out and then it pulls
Yeah,
back.
There's a
That's
suction
the-
back. Yeah.
Yeah,
Like
because
the
it's
rarefied
sucking,
side of the shock wave.
it's sucking back into the vacuum.
Yeah.
Yeah.
And you know, that's the effect we see at Tunguska with the trees splayed out in every direction,
right.
right? The shock forces have just mowed them down like a
Right.
bulldozer.
And was that one of the fossils that also had evidence of where they were saying like the state of the bones show that that there was burning while the flesh was still there? Is that also
No,
one
I
of
don't
those?
think they I don't
Okay.
know if they were looking at that, but yeah, I mean there are other.
Okay.
I mean, I think on Santa Rosa Island is where we saw that there was a mammoth,
Yeah.
and yeah, I mean lots of evidence because we're going to continue to talk about the evidence for global firestorms because that's
Right.
a big component of what happened. Because to me, what's fascinating is when we get into, you know, we're mostly dwelling upon the science here, but at the same time, we're going to look back because there are archaic traditions that I think are describing all of the kinds of things we're talking about here. You know, the fact that it comes down, you know, we have traditions that have come down from very olden times, very consistently from all over the world about this bimodal destruction of the world, this bimodal periodic destruction of the world by alternating flood and fire. But actually, when you look at the traditions themselves, there's more than a few where the flood and fire are actually part of the same process. And usually it's the fire that precedes the flood, which is very interesting. So we will push on. So anyways, this particular group, like the Compton, all out doing their independent evaluation, did report that all of the sites that they looked at, they did find the Younger Dryas Boundary spherules. And we will look at some of those examples of spherules that they found. Let me get back to here. All right. So here we have Younger Dryas Boundary spherules displaying some of the wide range of surface microstructures indicative of melting and rapid quenching. The top three are from the Topper site out in South Carolina that Brad and I visited with the boys, Chris Moore and head archaeologist of the Topper site.
Al Goodyear.
Yeah, of course, Al Goodyear. Yeah,
Mike
so
was there with us, and George Howard and Graham and Santha, and yeah, we had a crowd go over there.
Yeah, Mike was there, and I remember that day because on that day I believe that Mike became a little less normal. Okay, so the Topper site, right? So this is the Younger Dryas Boundary. The middle six are from Blackwater Draw, and Brad and I have visited Blackwater Draw. That's where near Clovis, New Mexico, which gave its name to the Clovis culture because the first studied Clovis site in North America was Blackwater Draw. And what was significant about the Blackwater Draw site was here was a mammoth skeleton found with a Clovis spear point embedded in the rib cage. So that was, so here's evidence that they did hunt them. Of course, the problem then was you find one mammoth with a spear point embedded in a rib cage.
Overkill.
Yeah, you extrapolate from that. Well, if they hunted one mammoth here, then they must have killed the entire species over the entire planet.
Right.
I don't see necessarily that one follows from the other.
Yeah, just because it's just what we do.
Yeah, it's just what we do.
Wanton slaughter.
Right.
That's our thing.
Right. So these six are all from Blackwater Draw. And notice the surface texture of these things. Again, what you're seeing here is a surface that melted and then crystallized. So this is what they're referring to as quenching. And so this is character. And the reason that they know that is because they've duplicated all of this in the laboratory by taking similar compositional material and melting it under high temperature and high pressure, and then studying the effects of as it cools and forms essentially the same type of a surface texture. And I'm sure I can find some examples of laboratory produced microspherules that have this same type of surface, what they would call a melting and quenching. Melt on the one hand, melt and quench. So quench is essentially the cooling off of it. But several things. Look at the second one from the topper side here. See how it's broken again?
Yeah, it looks hollow too.
And it looks hollow, yeah.
Yeah.
Mm-hmm. Then the bottom, as it says there, is the Paw Cove. It's an archaeological site on the coast of Talbot County, Maryland. The site, first identified in 1979, is a complex of 3 locations on 500 meters of shoreline on Chesapeake Bay, at which stone artifacts with an estimated date of 11,500 to 10,500 before Common Era have been found. Now, this is interesting. 11,500 before Common Era, means that you're counting before 2,000 years ago, right? So if you add that 2,000 years to the 11.5, you're right at 12.5. So what's happening here is they're finding stone artifacts showing up roughly between 300 and 400 years after the Younger Dryas.
That would be 13.5, right?
Yes, this would be about.
Yeah. 13.5.
Oh, so then they're Clovis. Yeah, they're Clovis, and then
Right.
12. So yeah, right in
Yeah.
there, right.
13 to 12.5. Yeah, 13.5 to 12.5.
But these are estimated dates. So then,
Yes.
yeah, excuse me, I retract that. I misspoke. Yeah, 13.5 would be, that would actually be Clovis then. Because
Yeah.
remember, the Clovis were pre-Younger Dryas Boundary.
Right.
And then the bottom one, as it says, is from this Paw Cove. And here, look at the middle one here. You've got a spherule, but it's been bombarded by all these much smaller spherules that, again, under high heat and pressure, just hit the bigger spherule, and then they welded together. And that's what you're seeing here. So this was part of Lecomte and Company's independent evaluation of conflicting microspheral evidence. And here's a framboidal spherule, which is a very different animal altogether. At these 3 sites, framboids are morphologically different but chemically indistinguishable from the apparently melted microspherules described in the foregoing. On the other hand, Israde et al. In 2012 reported that sulfur-rich framboids from Lake Cutzio, Mexico, are chemically different from the ones we observed. Now, see, the thing is that the framboids are presumed to be terrestrial in nature. And without these high resolution microscopes, you aren't going to be able to tell the morphological differences between those and a surface, for example, that we were just looking at, where you see this melt quench sequence there. See, so these things can actually have a pseudo organic formation. And some of the critics were saying, well, you just saw these framboids, and you weren't looking at something produced in an impact. You were just looking at these regular framboids that are found, throughout soil and so on. And then so what Lecomte and team are doing here is showing that no, what we're looking at is actually a very different animal.
Yeah, that's the scale of that thing is a lot smaller, isn't it? What does that say? 5 microns? The other ones are like 20 and 40. Oh, okay. I see. It might be 10 microns across.
This one is a 17
okay.
micrometers diameter framboidal sphere.
Small.
Yeah, I mean, some of the other ones were like 100 micrometers, and then there was even one that was like on a centimeter scale.
But notice that it's chemically indistinguishable. So what that suggests is that these microspherules that we're looking at are composed, a lot of it is from crustal material that's been ejected into the atmosphere.
Right.
So
and different quenching processes, probably, maybe.
Probably, yeah.
Result in the crystal growth being more pronounced in those rhomboids than the smoother spheres. I don't know.
So then another study, which we'll probably pick up with next week, but I don't know, we'll see. Maybe we'll get through it here. From 2013, James H. Whitkey. So this is another excellent paper that we're looking at here. It's called Evidence for Deposition of 10 Million Tons of Impact Spherules Across 4 Continents, 12,800 years ago. And they're commenting here, and they say air bursts by a fragmented comet or asteroid have been proposed as the Younger Dryas onset, based on identification of an assemblage of impact-related proxies, including microspherules, nanodiamonds, and iridium, distributed across 4 continents at the Younger Dryas Boundary. Spherules peaks have been independently confirmed in 8 studies, but unconfirmed in 2 others, resulting in continued dispute about their occurrence, distribution, and origin. And of course, we've talked about those other 2. But what happens is, as you get these multiple teams going out and looking, more and more people are actually and understanding better the protocols that you have to follow to find these things and where to look precisely. Once the improvement in technique has evolved, now you have teams that are going out and finding this stuff, right?
Yeah.
Let's see, to further address this dispute and better identify the YDB spherules, we present results from one of the largest spherule investigations ever undertaken regarding spherule geochemistry, morphology, origin, and processes of formation. We investigated 18 sites across North America, Europe, and the Middle East, performing nearly 700 analyses on spherules using energy dispersive X-ray spectroscopy for geochemical analysis and scanning electron microscopy for surface microstructural characterization. Using the term surface microstructural characterization, this is what we were just looking at in looking at the surface textures of these things, which shows the melt quench process. 12 of the locations rank among the world's premier end Pleistocene archaeological sites, where the Younger Dryas Boundary marks a hiatus in human occupation or major changes in site use. Our results, now this is another new team, following upon the work we were talking about last week and tonight. Our results are consistent with melting of sediments to temperatures greater than 2,200 degrees centigrade by the thermal radiation and air shocks produced by passage of an extraterrestrial object through the atmosphere. They are inconsistent with volcanic, cosmic, anthropogenic, lightning, or autogenic sources. So when he says cosmic, that's referring to this slow, steady, gentle rain of cosmic material that we were just talking about. We also produced spherules from wood in the laboratory at more than 1,730 degrees centigrade, indicating that impact-related incineration of biomass may have contributed to spherule production. At 12.8 thousand years ago, an estimated 10 million tons of spherules were distributed across 50 million square kilometers, similar to well-known impact strewn fields and consistent with a major cosmic impact event. Impact-related spherules have long been considered one of the most distinctive proxies in support of this hypothesis. However, despite increasing evidence for YDB peaks and impact spherules, their presence and origin remain disputed. In the latest example of this dispute, Boslow and others stated that, quotes, magnetic microspheral abundance results published by the impact proponents have not been reproducible by other workers. However, the authors, being Boslow and others, neglected to cite 9 independent spherules studies on 2 continents that reported finding significant YDB spherules abundances as summarized in high-profile previously published papers, mentioning papers we have now looked at by Israd et al., Bunch et al., and Lecomte et al., all of which we have now looked at. The 9 additional sites are located in Arizona, Montana, New Mexico, Maryland, South Carolina, Pennsylvania, Mexico, and Venezuela. We've not talked about the Venezuelan evidence yet, which is very important and quite interesting, actually, because with the discovery in Venezuela, the geographic range of this phenomena got extended considerably, just as with the discovery of Younger Dryas Boundary proxies in Syria, you see. And so part of the idea here is, well, we know now that it covers a large portion of the Earth's surface. What's the limit of it? We don't know. But what's happening is as the studies move further and further out away from North America, and we keep finding this stuff. Like, let's see, right here, an interesting paper that I have been reading this last week. Yes, okay, so this is the paper. Is it going to be backwards? No,
we can see it.
Okay, good.
Antarctic.
Did the black matte impact airburst reach the Antarctic? Evidence from New Mountain near the Taylor Glacier in the Dry Valley Mountains. Their conclusion is, yes, it did reach the Antarctic. So there we go. I mean, it's like we're looking and we're finding that more and more that the extent of this phenomena is just growing to encompass ever larger portions of the planet. So
what are we going to do next week?
Well, we'll pick up and continue, and then we're going to come back around to the evidence. We want to talk about Wolbach's work and her team looking at extraordinary evidence for biomass burning, because that's important, because we want to get clear on all this stuff so we can get the scientific perspective on this. Then when we go to some of the more traditional accounts that have come down to us from centuries or millennia ago, we can kind of have this framework of understanding to help us see that we're not just looking at some contrived superstition or some exaggeration of some local phenomena that somehow, there was a big forest fire or whatever, or just in the same way that there was a large local flood that somehow was so embedded into this, to the consciousness of the people, into the psychic life of these people, that it was literally perpetuated for thousands of years. No, I think we have to really consider the idea that we're looking at something on a much grander scale that has left its imprint in the in the mythological record of the human species. And so by looking at these in detail at the scientific models of this and using that as a framework, I think then we will be in a privileged position to be able to look at some of these ancient accounts with a new light. So that's one of my goals here, and why I'm trying to delve into some of this stuff to such detail. So I'm hoping that a lot of the people that are tuning into this love the detail, getting into it, because look, the devil is in the details, and we're trying to tease out the devil from all of this, the metaphorical devil, right? And then
no, I think the point of this podcast is definitely to get all the details. I really think that's what people want.
Good.
I know that's what I'm enjoying for sure, is to really hash through all of it. Every single slide, Randall, all 10 or 20,000 of them, every slide, every one.
Well, we'll try to get at least 10,000 of them next episode.
Okay, good. All the details.
All the details, yes.
I'm here to get just a general overview.
Well, that's important too. But for some of us who are a little bit more fanatical, the appeal of this to me is in the details, because really what we're engaged in is sort of a forensic investigation here of this event, this thing that happened. If you want to look at, say, let's if we want to anthropomorphize it or personalize, let's say we're investigating the murder of the great megafauna.
Right.
That could be that
cool.
could be
And that's a
one-
reason to do forensics for sure.
Yeah. So what killed the megafauna? Who
Yeah.
killed the megafauna, right? Or what, so that's one way of looking at it. Were humans responsible? These overzealous human hunters raging over the landscape, slaughtering everything in their path, so fast that a few, tribes consisting of maybe a few dozen to 100 people scattered widely over the surface of the earth were able to exterminate every last individual of these extinct species
and then disappear themselves
disappear themselves. Yes, exactly.
with,
Good
with
point.
no evidence of the millions it would have taken to slaughter millions of mammoths.
That's what murderers do. They show up, they kill somebody, and they disappear.
Well, and then
That's their
like
job.
all good forensic detectives, we're going to be looking and are looking at both the footprints and the fingerprints. And as I
Right.
kind of defined it before, the footprints are the things that we can see in the landscape. We can see, we don't need microscopes to see them, right? The fingerprints are the things we don't see immediately. We don't see those microspherules,
Right.
in the dirt. We don't see those without. We have to use technology. We have to use scientific instruments to detect that.
All right, gentlemen, that was a great show. Brad, any video channel updates? Anything else?
Oh, subscribing is free, so please subscribe and
There you
share at will. Yeah, the numbers are going up, but we need a whole lot more numbers. So,
I have seen that the numbers are climbing, which is always good.
yeah,
Well,
But yeah,
some great comments and some very supportive comments and some interesting little trails of conversations going on there. Yeah, good stuff.
Yeah, I want to express my appreciation for everybody who's been tuning in, all the patron supporters that are helping us out here. And, we're doing our best to get this act together and, provide some special stuff for people that are really giving us the support. And it's going to happen. But I'll also mention, we're joining forces with some interesting things that are happening. People don't know yet about how to, but that's going to be something we learn about soon. And we got a new website coming within the next week or two that's going to be quite spectacular. And I think people are going to really find some really interesting stuff there, and including all of our podcasts. And but it looks like the September Scablands tour is
still on.
Still on,
And we're still, people are signing up for the second week, so keep on letting Darren know if you want to go.
That's right.
We're looking for the second week to be viable, and that we should know that within the next couple of weeks. So
Mhm.
if you want to go, set up a spot with Darren, because
Mhm.
we may have a second week available. And yeah, we're running long here, so everything's in the show notes, all the links. Email us, cosmographia1618@gmail.com. Thank you guys very much. We'll see you next week.
Thank
We
you.
appreciate all the support. Good night.
Good night, everybody.
Ciao.